All right, let's dive way back. Way back to the very dawn of artificial intelligence. We're going to talk about one of its most important, most foundational ideas, the perceptron. It sounds kind of technical, but trust me, it's a simple idea that literally sparked a revolution. And, if you want to understand how AI even started to think, you've got to understand this. So, let's get into it. Okay, so the whole story really kicks off with this one huge question, a question that totally obsessed the first AI researchers back in the 50s. Forget all the complicated stuff for a second. The real puzzle was this. How on earth can you teach a machine to do something super basic? Like just classify things. Tell the difference between two objects. Is this a cat or is it a dog? An apple or an orange? This was the big problem. The one a psychologist named Frank Rosenblatt decided to tackle head-on.
So, where do you even start with a problem like that? Well, these early pioneers looked for inspiration in the most powerful computer they knew of, the human brain. The blueprint for their thinking machine, it came straight from biology.
And what they created was the perceptron. Now, what is it? Think of it as an artificial neuron. It's basically a super simplified mathematical model of a single cell in your brain. You know how a neuron gets signals, processes them, and then decides whether to fire or not? Well, the perceptron was built to do the exact same thing. Take in data, weigh all the evidence, and then make a simple final call. Yes or no. It was an absolutely revolutionary first step.
But oh man, its history was a total roller coaster. When Rosenblatt first showed it off in 1957, the excitement was off the charts. People thought, this is it. Truly intelligent machines are right around the corner. But then, bam. In 1969, this famous book, literally called Perceptrons, came out and exposed a huge, fatal flaw. We'll get to that for sure. And it just put the brakes on everything. It kicked off what we now call the AI winter, where research just cooled off for years. But fast forward to today, and its legacy, it's totally secure. We now see it for what it is, the granddaddy of all modern neural networks.
So, how does this little artificial neuron actually work? What's really going on under the hood that lets it make a decision? All right, let's break it down and look at its anatomy.
Okay, you can really think of a perceptron as having four main parts. First, you've got your inputs. That's just the data, the information you're feeding into it. Then, each of those inputs gets a weight. Now, the weight is super important because it's how the perceptron decides how much to care about each piece of info. After that, there's something called a bias. It's kind of like a thumb on the scale, just to give the model a little more flexibility to make the right call. And finally, the whole thing gets funneled into the activation function. That's the final decision maker. It takes everything in and spits out the final verdict. Yes or no, 0 or 1.
And the way it works is actually pretty straightforward. Step 1, the perceptron gets all the inputs. Then, for step 2, it multiplies each input by its weight and adds it all up. This is basically its way of weighing the evidence. That final number, the weighted sum, gets passed to the activation function. And the activation function has one simple job. Is this number bigger than my threshold? If yes, it shouts 1. If no, it outputs a 0. That's it. Simple as.
So what's all that math actually doing? Well, if you think about it visually, it's doing something surprisingly simple. It's drawing a line. That's it. Imagine you plotted all your data as a bunch of dots on a graph. The perceptron's entire job is to find the one perfect, straight line that can separate the two groups of dots. And that line, that's what we call the decision boundary. Okay, but here's where the real magic comes in. This is the part that changed everything. The perceptron wasn't just some static calculator. No, it was designed to learn. And the way it learned was just brilliantly simple. It learns from its mistakes.
And this is really the key takeaway right here. If the perceptron gets an answer right, it does nothing. It just moves on. It only adjusts itself, only changes when it makes a mistake. Think about how efficient that is. Why fix what isn't broken, right? It's only when it gets something wrong that it says, whoops, okay, I need to tweak things. So how does it actually change? Well, it uses this little formula called the weight update rule.
Whenever there's an error, this rule kicks in and makes these tiny, tiny adjustments to the weights and the bias. Remember that decision boundary line we talked about? Think of this as just nudging it, tilting it a little bit, shifting it over, just trying to get it a little closer to the right spot. And it just keeps doing this over and over. Every time it messes up, it nudges the line. And here's the amazing part. For certain kinds of problems, this process is guaranteed to work. It will find the perfect solution. But, and this is a huge but, there's one massive catch. The data has to be what we call linearly separable. All that means is that a perfect straight line to divide the data has to exist in the first place. And that one condition, that need for a simple, straight line, that would become the perceptron's most famous, and for a long time, its fatal flaw. It was, quite literally, a line it couldn't cross. So here's the bottom line. If your data points are messy, if they can't be perfectly split by one single straight line, the perceptron fails. It just can't do it. It'll try forever, nudging its little line back and forth, but it will never, ever find a solution. And, as it turns out, a lot of problems in the real world, they just aren't that simple. And the classic textbook example that completely stumped the perceptron is a really simple logic problem called XOR. It just stands for exclusive OR. The rule is easy. The answer is true if one thing or the other is true, but not if both are. You can see how it works in the table. It creates this kind of tricky diagonal pattern. Okay, now really picture this. Imagine these 4 data points on a graph. You've got 2 zeros and 2 ones arranged in a square. So, go ahead, try it right now in your head. Can you draw one single straight line that puts the 2 ones on one side and the 2 zeros on the other? Give it a shot. Spoiler alert, you can't. It's impossible. No matter where you draw that line, horizontally, vertically, diagonally, you are always going to have at least one point on the wrong side. And this simple but totally devastating observation is exactly what Minsky and Papert pointed out in their famous 1969 book. It proved that this amazing new model had a hard limit. And that realization, it sent a real chill through the entire AI community. But that's not the end of the story. Not even close. Because even with this huge flaw, the core ideas that the perceptron introduced were just too powerful to ignore. They laid the groundwork for literally everything that came next. I mean, its legacy is just immense. So let's just recap what it gave us, right? The whole idea of weighted inputs, that some information is more important than other information, that came from the perceptron. The revolutionary concept of learning from your mistakes, of error-driven learning, that was the perceptron. The visual idea of a decision boundary, perceptron. These ideas aren't just history, they are the absolute heart of machine learning today. It's why it's still the perfect first thing you learn about when you study AI. So what was the solution to that pesky XOR problem? Well, it turned out the answer wasn't to throw the perceptron away. It was to stack them. See, one perceptron is like one brick. It can only make a straight line. But what if you stack a bunch of them together in layers? That's what modern deep neural networks do. By stacking them, they can create complex, curvy, nonlinear boundaries and solve all sorts of insane problems, from recognizing images to understanding human language. So when you look back, the perceptron's real value wasn't about what it could do. It was about what it represented. It was this huge conceptual milestone. It was the first time we had a concrete model that showed, hey, maybe a machine can learn from its experience. And that single idea is what continues to drive the entire field of AI forward, even today. Which kind of leaves us with one final big question, doesn't it? The journey from this one simple little artificial neuron to the mind-bending AI we have today has been absolutely incredible. So it really makes you wonder, if this was step 1, what in the world will the next million steps look like?